Hi, and welcome to this look at a 6-mark leveled response question on the oxidation of butane. So looking at the question, as it's a 6-marker and it's unstructured, you need to think a little bit about how to plan out your answer. So it asks you to describe the oxidation reactions of butan-1-ol forming an aldehyde and a carboxylic acid. So you need to include both of those, and I would use equations rather than lots of words to describe what's going on. And it says, explain using a diagram how the aldehyde can be produced in the laboratory by controlling the reaction conditions. So you'll need the reaction conditions and a diagram to show how this is done. And obviously, because it's going to be distillation to separate out the aldehyde based on its boiling point, this is the apparatus you'll need to draw. So once you've done your plan, you can think about how you're going to construct your answer. Now there's two strands to your answer. One is the description of the oxidation reactions, and the other is the explanation using a diagram how the aldehyde can be produced. So you need to have two separate sections to your answer to encourage you to try to develop them together. So first of all, let's do the oxidation reactions. I'm going to start with the partial oxidation of the alcohol to an aldehyde using O in square brackets to represent the oxidizing agent. I'll talk about what that particular oxidizing agent is in a moment. So you make an H2O on the right hand side. It's always a good idea to just count up the carbons and hydrogens and oxygens on both sides to make sure that they're balanced. And you can use O to balance on the left hand side for oxygen and H2O to balance on the right hand side for hydrogen. Now clearly, the further oxidation of the aldehyde once it's been formed involves the use of another oxygen atom. So therefore, this time round it turns into CH3, CH2, CH2, COOH, which is butanoic acid, and notice there isn't another water molecule produced. So when you do the overall equation, you keep one water molecule in the products, and you have two O atoms this time because you're combining these two together. So the reagents and conditions and observations for the partial oxidation is the distillation with acidified potassium dichromate. And the orange solution that is at the start will turn green, just give you a visual clue that the reaction is proceeding. For the further oxidation, you want it to completely oxidize from the aldehyde to the carboxylic acid, so you reflux it. In other words, you heat it for longer, and you don't distill it, so you have the refluxing condenser mounted vertically. I'll do the diagram in a second to show how the refluxing condenser is mounted when you do distillation. So I'm just going to get... So on this slide we've got the reagents and conditions and observations for the full oxidation of the alcohol all the way to a carboxylic acid. So this is essentially a combination of these two. So you've got two O atoms from the oxidizing agent, which again is K2Cr2O7, must be acidified, and the orange solution again will turn green as the oxidation proceeds. So clearly you can see that the diagram is set up for distillation because the aldehyde has a lower boiling point than the carboxylic acid. So therefore we also need to label up the diagram. So I'm just highlighting which reaction we're referring to now. So in no particular order, the pear-shaped flask contains the anti-bumping granules to control the rate of reflux and distillation, I should say, and the reaction mixture is obviously in there as well. You have a still head connected to a condenser, which is set up with a conical flask to collect the distillate. Obviously, there's a thermometer, and this will measure when the boiling point of the aldehyde will be reached, so when to expect to collect the distillate in the conical flask. Okay, I hope this has been a useful look at one way of putting together an answer for this question. Thanks for listening. Until next time, see you soon.